So let me start with the basics of air conditioning, because you got to understand how the system works in order to understand what's going to go wrong. So now, keeping a small boat cool is really not that difficult to do. As a matter of fact, you can do it basically with a cooler and a 12-volt fan, because all you're doing is blowing warm air over a cool surface in order to get cool air out the other side. So you can take a Coleman cooler, you don't want to take anything expensive, and cut a hole in both ends, fill it full of ice, and take just a 12-volt computer fan, bolt it to one side, plug it in, and tra-la, you have an air conditioner. It's going to cool off a small space. And for a small cubby cabin or the V-berth on a small sailboat, on an irregular basis, that's not a bad idea. But over time, it's going to get expensive because, oddly enough, that ice is just going to keep melting on you. That's the way ice is. So our next step up would be to go out to Walmart and get a little 5,000 BTU air conditioning unit and attach it to your boat somehow, either through an opening in the companionway or down a hatch or something. And I did that for years. I actually cooled our 45-foot boat with two window units, two 10,000 BTU window units, one over a hatch in the forward end, one over a hatch in the aft end, plugged in just into the 120-volt system. And that works, as long as you don't actually want to move the boat at any point. Because to get that to work right, once you put the air conditioning in place, you then have to figure out some way to direct the air into the boat. And I've done it with poster board, I've done it with foam board, I've done it with foam core, I've done it with plywood. And each system gets a little bit more expensive. You go with poster board. Poster board's nice and cheap until the first time it rains, and then you got nothing. Plywood is great. You could have the boat fall on it, but once it's in place, it's probably heavier than the air conditioning unit itself. And while you're doing all this, you've got to seal everything. And you can use permanent seals or you can use temporary seals. If you use permanent seals, you can't take it off till the end of the season. If you use temporary seals, then it's never going to be 100%. But it's cheap. It is. You can buy a 5,000 BTU air conditioner at Walmart for less than $100. Now the next step up is a unit that Dometic makes. It's a hatch, drop-in hatch air conditioner unit. Weighs about 75 pounds, and you just open up a hatch, drop this thing on. It's got a hood that you can put in and plug in, and the system just runs like a champ. It's $1,200. Okay, that's a significant step up from $100 from Walmart, but you didn't have to do the engineering. It's self-contained, so you can take it off and just throw it down below. And it probably will last you about 10 years, where the one from Walmart will last you about 1 year. So actually, if you think about it, yeah, you're spending $1,200 for something that's going to last 10 years rather than $100 a year. It's probably going to balance out. But again, that's not necessarily going to be helpful when you want to get away from the pier, because now you got to find some place to store that. And so now we get up to the level that we're talking about here, which are installed air conditioning units that are actually bolted in and water cooled. So let's start with how does this thing work? Well, over on this side, we have what's called the evaporator. Now, the evaporator is basically the same thing that we had in our little cabin cooling ice chest. We have a set of coils, and we have a fan. And that fan is going to blow warm air across a set of coils. There's going to be a cool liquid inside there, and the heat from that warm air is going to transfer to those coils and come out cool. Now, just to pick a couple of numbers at random, let's say that the air coming in is 90 degrees Fahrenheit, and the air coming out is 70 degrees Fahrenheit. So what we have with that coolant moving through there, by the way, that coolant is referred to as refrigerant, but you'll hear a lot of people refer to it as Freon. Like, I got to replace my unit, the Freon leaked out. Freon was a product created by the DuPont family, by the DuPont Corporation, not actually the DuPont family. It's not like the DuPont family was sitting around dinner one night and go, you know, here's an idea. We could make a refrigerant. No, it was created by the DuPont company, and it has a very specific set of characteristics that make it do very well as a medium for transferring heat in and out of this system. The problem with it is that when it leaks out, it's very bad for the environment. So several decades ago, they stopped making Freon. And now there's a bunch of non-ozone depleting refrigerants. And these refrigerants all start with R, and they have a number after it. R134, R140, R410, all of these things. It's wonderful. But much like halon firefighting agents, which aren't halon anymore, we're going to end up referring to the stuff inside here as Freon, even when it's not. Interestingly, there are some units, some old units, that can only use actual Freon. And the only way you can get actual Freon nowadays is somebody will have an old Freon unit, and these are usually industrial units, and rather than release the Freon to the atmosphere when the system gets broken, they will suck all of the Freon out, store it, recirculate it, clean it up, and resell it. So any Freon, actual Freon on the market today has actually been sucked out of some old unit and cleaned up to be refreshed. You're not going to have Freon on your boat. You're going to have some sort of refrigerant. Okay, so this refrigerant is now moving through these tubes, and if we want to get a 20-degree delta T is just an expression. It's one of those engineering things where engineers get to sound really cool. Delta T simply means difference in temperature. By the way, a difference in pressure is a delta P, and we'll talk about delta Ps in this system later. So the delta T across this is 20 degrees. In order to get a 20-degree delta T across the air, we've got to have a greater difference across the refrigerant. So we're going to say that the refrigerant coming in, let's say it's coming in at 30 degrees Fahrenheit, and it's going out at 60 degrees Fahrenheit. So we got a 30-degree delta T across the, and I'm making these numbers up. I'm just using random numbers here. Don't go down to your boat and go, oh, Frank said that would be a 30-degree delta T, and it's actually a 40-degree delta T. Just understand that we're using these numbers, okay? So, and I know that somebody in the back is sitting and thinking, well, 30 degrees is less than freezing, so it's not going to work. That's the thing about refrigerant. Refrigerant at certain pressures can actually be less than freezing, the water less than 32 degrees, which is the freezing temperature of water. Okay? So, we got 30 degrees going in, we got 60 degrees going out, we got 90 degrees air coming in, we got 70-degree air coming out. It's nice and cool, we're very comfortable, yay us. Well, but now we've put that heat into the system, how do we get it out? Well, amusingly, we have another heat exchanger. This is a heat exchanger. This is a heat exchanger. This heat exchanger we're going to call the condenser. Now, evaporator means that when something evaporates, it goes from a liquid to a gas. When something condenses, it goes from a gas to a liquid. So amusingly, what's happening over here is that we're putting a fluid in here, it's getting warmer. We're putting a fluid in here, it's getting colder. Now, in your basic home air conditioning unit, this is cooled by air. If you got a heat pump, there's that big thing outside your house, has a big fan in it, bunch of coils. That's the condenser for that system. On your air conditioning in the little wall unit, this is the part that's outside the house and is blowing the warm air out. Okay? So in a home air conditioning unit, it would be exactly the same. We'd have this fan over here blowing air across that coil. In a marine air conditioning unit, we actually have a much better fluid to cool the system down or take that heat out. It's seawater. Seawater, or river water in our case, will accept significantly more energy for the same flow, or will accept a much better flow rate, or will allow us to have a greater delta T for the flow rate that we're dealing with. So on this side, rather than having a fan, we got a pump. And the pump is taking a suction from whatever we're sitting in, pumping the water across that set of coils, and then pumping it out the side of your boat. And yes, there's more pieces to that, and we'll talk about the more pieces to that later, but this is the basics, okay? So we've got a heat transfer over here, we got a heat transfer over here. Now, on this side, let's say that our water temperature coming in is 70 degrees, and our water temperature going out is 90 degrees. So we got that same delta T of 20 degrees. The problem is, in order to get heat out of that system, it's got to be warmer than 90 degrees going in. Because if we pumped in that 60-degree water at that point, what we'd be doing is taking heat out of the river and putting it into the boat, which is kind of the opposite of what we want to do. So now, what we got to do is we got to get the temperature over here up to 100, so that after we run it over these coils, we can get it out at 80. Wow. So I got to get this 60-degree temperature up to 100 without actually adding heat to it. Because if I add heat to it, then I'm just making the system less efficient. Well, okay, back in my Navy days, we used to refer to a system that just worked and we didn't really understand why as PFM, pure freaking magic. Now, of course, back in my Navy days, we did not actually use the term freaking, but this is a mixed company and I've gotten older in my worldview. But anyway, pure freaking magic. It just works. Well, here's part of the magic. Up here, between these two parts, we're going to add a compressor. Now, what this compressor does is it takes the pressure, it takes that fluid coming out of the evaporator and it compresses it. And when it compresses it, it raises its pressure, and when it raises its pressure, it's raising the temperature. because what it's doing is it's taking all those little molecules in there and putting it in a tighter and tighter space. And when it's in a tighter and tighter space, the molecules are bouncing off of the surfaces, and it raises the temperature. So this compressor is doing two things. First off, it's raising the pressure in the system from one side to the other. So over here we have the low pressure side. Over here we have the high pressure side. And the first thing that's doing is compressing that liquid and raising its temperature. So we raise the temperature across that without actually adding heat to the system. Well, there's a small amount of heat added because of the compressor, but for the most part, it's just that process that's raising the pressure and temperature. So now we've got it coming into here at the temperature we want it, and it's coming out at 80 degrees, but hey, we wanted it at 30 degrees. Now how are we going to get it to cool back down? Well, this is where the M part of the PFM comes in. Anytime we have a system under pressure, this is a liquid in here. You can actually hear the liquid bouncing back and forth. Anytime we have a system under pressure, this particular can right now is 69 degrees. But if I start to release the air from this, I'm taking it from the high pressure inside the can to the low pressure in this atmosphere, and I can actually feel the temperature of the can coming down. Okay? The temperature in this can, which was 69 degrees when I started, is now down to 35 degrees. It's cold. If I keep doing this long enough, I'll actually get frost on the can. All I'm doing is taking high pressure and releasing it into a low pressure, and that action where everything expands causes the system to give up heat. That's the piece down here that connects it. This is what we call the expansion valve. And all the expansion valve is doing is connecting the high pressure system and the low pressure system in such a way that as it moves across that expansion valve, it expands, the pressure drops, and because of that, the temperature drops from the 80 degrees on this side to the 30 degrees on this side. Okay? Now, on a home air conditioning unit, that's actually a valve. And it has a little control in there. And the little control is attached to something else that senses the temperature in the room and tells the valve to open or shut, more or less, in order for the system to work. On our marine air conditioning units, we don't have to go to all that trouble. And because of that, when we take a look at the actual real-world air conditioning units, you'll see that this is a much simpler system than having a valve. Okay? So that's basically what's happening. All we're doing is compressing the refrigerant, giving it a lot of heat, running it over a set of coils where we take that high heat to a slightly lower heat. We run it through a system that decompresses it, and when it decompresses it, it releases all of the excess energy, pulls it back up the other side, uses that cooler fluid to cool off the air, and the system just keeps working. So let's take a look at two real-world air conditioning units. Over here, this is a 12,000 BTU unit made by a company called Mermaid Air out of Fort Myers, Florida. It's actually owned and operated by the family that started the company years ago. And they make air conditioning units for boats and for emergency medical services vehicles. Basically, ambulances need to keep certain things cool, and they make air conditioning units that work in there. In this unit, this area up here is our evaporator. It has a set of coils. It has a fan. And the fan blows, actually sucks warm air through this set of coils and up to a discharge vent where it then goes out into the rest of your boat. This set of tubes here is the condenser. Now all they've done is they've taken one tube and run it inside the other tube. So the water, seawater, will come in through this hole, pass around the outside of the inner tube, and come out this side and get pumped over the side. Inside there, there's a second set of tubes that have the refrigerant inside of them. And the refrigerant is moving the opposite direction of the coolant, of the seawater. So basically the refrigerant, where the seawater is coming out the top, the refrigerant is going in at the top. And the refrigerant is coming out at the bottom. Now over here, this is our compressor. And the compressor is generally the biggest and heaviest part of the air conditioning unit. This particular compressor also has a canister attached to it, and that canister is designed to collect this fluid so that the compressor is actually working with a liquid. So this area right here allows the gases to condense into a liquid so that the compressor is dealing with a liquid fluid instead of dealing with a gas. Okay? And coming out of, if this is the compressor, this is the condenser, and this is the evaporator, well, where is the expansion valve? There are two very thin lines right here. These two very thin lines are the expansion valve. It's not on a marine air conditioning unit in a size generally acceptable for boats our size. That's all the expansion valve is. They're taking the big hose that's coming out of the condenser and running it through very small tubes and into the evaporator. And when that gets into the little small tubes and then comes back out and expands again, that's where all of your cooling is taking place. This spot right here is where you're getting that release of gas. Okay? That's the system. Everything else is details. That's the system. Okay? Now, over here, this was manufactured by Cruisair, or it was a Cruisair unit. It's manufactured by Dometic. Dometic actually bought Cruisair and a couple of other companies, and so now all of their stuff is being made under the Dometic brand. Okay, this particular one is slightly more advanced, and it's larger. Where that is a 12,000 BTU unit, this is a 16,000 BTU unit. Okay, but if we actually look at the size, this is a lot larger than the evaporator on this one. This one has a much smaller evaporator, but the tubes themselves are smaller and there's more of them passing through there. Okay? Again, we have the evaporator. We have the condenser. The condenser is also double wrapped. In other words, there's an outer tube and an inner tube. The water flow is going in the bottom, coming out the top. The coolant flow is going in the top and coming out the bottom normally. We have a compressor. We have a canister where the material can come up. And on this particular unit, because it's slightly larger, instead of having 2 small lines, it's got 3 small lines. But other than that, the expansion valve works exactly the same. Okay?